Hello, everyone. This is Dharma Katyura. I'm a physics faculty at Kentucky State University. I'm trying to share one interesting physical process, physics, something that can be a little bit explained by, I would say little bit explained by physics. And that mostly it is a natural process we observe in nature that can be observed in nature. So let me just share you something about that physics phenomena. Okay, so for that, let me share my screen. Okay, share my screen. I'm just going to share my PowerPoint. And if you have any question, if you come up with any question, then make sure you send me email. I will provide my email and address at the end of this presentation. So let me start with this, the title. It is Synchronization of Oscillator in Nature. So something we observe in nature. We are talking about oscillator. So I'll just share you some basics of oscillator. And the key thing is synchronization. Okay, so I think there are other words, similar word in place to replace synchronization. We can say like collective behavior. So common behavior, right? So we are, of course, when we talk about synchronization, we are dealing with many oscillator. So it's just not just one oscillator. So that we are going to learn, right? And this is my outline. I will give you a basic definition of oscillation and oscillator. Then we'll just touch phase oscillator. And these keyword, oscillator, basic physics of oscillation and phase oscillator, these words should be enough to describe synchronization phenomena. And we'll also try to see if there is any mathematical model that can explain synchronization. Okay. Now let me go to another slide. So this synchronization, we don't know its clear picture yet. So I'm going to elaborate synchronization, but we observe this phenomena in our real life. There are like a biological system that exhibits synchronization, like collective behavior. We do observe this thing in chemistry and some experiment in physics. Also in social system, that's very interesting. And there are so many mathematical model currently presented to describe these natural phenomena, but not yet successful explanation of this natural process. We'll talk about its positive and drawbacks, positive side and drawbacks of this mathematical modeling. So before we get clear picture of synchronization, let's talk about oscillate. What is oscillate? Like a swing, it's just oscillating or repeating same type of motion in certain interval of time. If you are familiar with, if you have seen pendulum clock moving to and fro motion, so that type of motion can be considered as a good example of oscillate. So pendulum is called oscillator and the motion is called oscillatory motion. So it is periodic motion, a repeating motion. Okay. So let's just, I need to introduce this idea of phase. If you are not comfortable with word phase, then you can simply say angle. Okay, and I need to bring a connection between angle and frequency. We'll talk about that maybe after a couple of slides. Well, let me just share a web page here, definition of something related to oscillator. Let me play this video. See here let's just call the first diagram movie clip with k is equal 1. See these dots are moving randomly. They are not controlled by each other. In second case, some of them moving collectively together, some of them not. In third case, they are perfectly moving in synchrony. And this is what we call synchronization. But right now, my intention is to feel you comfortable about angle. So angle made by these oscillator somehow depend on the frequency. Okay, so how often they rotate, that is called frequency. So the angle is related to frequency, and for now, we can simply stick with this plain definition. So theta we normally use as to represent angle, and omega, or you can also call W, this is a symbol of frequency. Angle is related to, there is a dot, means angle over time. How is angle changing? So if something is moving in a circle, like oscillatory, how is angle changing over time? That is represented by theta, and there is a dot. Okay, so if you are not familiar with calculus, then just feel like angle changing over time is equal to frequency. So how is angle changing over time? That gives how many cycles a particle is making in a circle while moving around a circle. So that's a basic physics, mathematical, a basic formula from physics. And we are going to use this idea here to explain it mathematically. Okay, so what is synchronized? That's the key thing to gain idea. Synchronization is, okay, so let me share you a video at first here. Let me share this video, clapping audience. I'm going to play here. I know it's a pretty loosely defined task, but on the other hand, I do think that I think I'm also sharing sound. So it's just like a clapping experiment. Somebody telling audience to start clapping. Okay, so what happens? Let's just try to feel it. It's basically simple that you all get it. Maybe so I can start. Just want to start clapping. Okay, now synchronize. So what happens here? Initially, there are many people. So when I use word oscillator, means it does not need to be like a pendulum. It can be any periodic event that is occurring at equal interval of time. So these audience, then these people they started clapping. So when they start clapping for maybe a couple of seconds, the sound is incoherent. It means there is no rhythm, right? But when after some time, they automatically the sound automatically becomes like harmonic, or the sound automatic, that the clapping, the sound coming from clapping, that automatically gains some harmony. Means it is synchronous. That's why I'm using word synchronous here, in a rhythm. Initially, it does not happen. It takes some time, but that some kind of rhythm is formed after some time. Now, let me just play for a second. Now there is a synchrony, there is a harmony. So everybody is clapping collectively. No one is there to tell them, now clap, now start. There is no one. Once they start, yes, there is some mismatch at the beginning, but it gains some rhythm after some time. And this is called synchronization. And it's not due to any forces, any command. Nobody is telling us to start clapping, stop. Nobody is telling once we start from the beginning, right? So this is one example of synchronization. Now, what is exactly synchronized? Now, based on that observation, we can probably draw some conclusion. So it is called, systematically, we can understand synchronization like this. Adjustment of rhythm of oscillating object, means the person who is doing clapping, due to their weak interaction with each other. So they somehow, individual people, somehow they manage to they manage to keep the clapping synchronous with each other, but it's not due to any central command. Nobody is telling us to do in every second, no. So it is like self-organization process. So I already mentioned this word. There is no any central force. Nobody is telling us to start clapping, stop clapping, no. And we are dealing with many oscillators, means many people are involved there. So when we talk about synchronization, we are not just focusing on few of them. We are trying to see collective behavior, right? Clapping audience, one good example of synchronization that can be observed in nature. Naturally, that can be demonstrated. And there are other interesting examples, synchronously flashing group of fireflies. I'll try to elaborate this thing in next slide. And birds in a flock, that is also a synchronized behavior. And even like this is interesting, it's a biological thing. Even the menstrual cycle of women are also becomes synchronized. Like let's say two female are staying in a home. That's this cycle, this phenomena is purely biological thing. It's not just happening due to the interaction between two persons. No, it's just spontaneous thing. But interesting thing is, if they are staying there for a long time, these cycles are the duration of these cycles are coinciding with each other. That is what we call synchronization. That's interesting. And probably you heard about London's Millennium Bridge. It's just like a synchronous behavior because many people were crossing bridge at the same time. So bridge was a little bit oscillating, but because of the synchronous behavior, synchronous motion of all individual, there was excess vibration in breeze, and that ultimately collapsed. So that was also that is also a good example of the related caused by synchronization. And Tacoma Narrows Bridge, if you have not heard this thing, then just Google it. That is also something interesting based on synchronization event. There are other examples like rhythmic response pattern of pacemaker cells in the heart. They are also, these cells are also synchronously behaving. And Parkinson's disease, like synchronously firing of many neurons, result in tremor, and that is also just one good example of synchronized. Okay, so we went through clapping audience. Now let me show you this thing. So these, the picture quality may be not so good, but these are all male fireflies. I heard that we observed this type of display in a couple of national parks in US. So especially these firefly, they are native of South Asia. Male fireflies, they just gather in a tree in like an evening time. They biologically, they are trying to attract female. So they start flashing. At the beginning, their flashing remains totally incoherent. No, they are not catching any rhythm, but after a certain time, their flashing becomes synchronous. So they are flashing at an equal interval of time. Most of these fireflies are flashing at the same time. So it becomes very interesting, attractive display. And I heard something like that type of display was used as a navigation tool in early time. So this is also a biological phenomena we observe in nature that can be explained by this synchronization. Okay, we have another example: bird in a flock. So their motions are so coordinated with each other. So this can be also one example of synchronous behavior, synchronization pattern. Let's go further. Now, these are the, is there any mathematical modeling, like can we describe, can we explain these phenomena mathematically? Of course, these phenomena are occurring naturally. So, but is there a way to explain them mathematically? There is one person, notably the Japanese physicist, I think he's not a physicist, I think he's a chemist. So his name is Kuramoto. He proposed a mathematical model to explain these natural phenomena. And this is what we call Kuramoto model. Theta, if you are not aware of word phase, then just consider angle. So angle are like, okay, per pendulum like thing, we can use word angle, but for fireflies, what's the meaning of angle? No, so I'm not using theta, just to represent angle. It can be any periodic event, okay? So flashing on and off, that can be considered one as a periodic event. And that periodic event has to do with frequency. So how frequently that periodic event is happening. That's why, so let me just call theta by, let me just use word periodic event for theta, and omega, or you can also call W, that is just frequency. So if these are like fireflies, if they are flashing independently, then we can use this simple mathematical definition, mathematical term, connection. So I am using, since we have many oscillators, so I can be 1, 2, 3, 4, maybe 1,000, maybe 10,000, maybe more. So that's why I'm just using a subscript I. I stand for individual oscillator, and omega or W is their respective frequency. So if these fireflies are flashing independently, let's say, then they are just, so their flashing event, their individual flashing event is just related to their own frequency, no connection with other fireflies. So for that situation, we can use this simple relation. But this person, Kuramoto, is emphasizing that there is some kind of coupling, now interaction, let's call. So we are, let's say two oscillators are like two fireflies are flashing light. So at some point, after a certain time, there occurs some interaction. So maybe one firefly adjusts timing by looking another firefly. So in language of math or physics, we use word interaction. So we more commonly we use word coupling. So there occurs some coupling between these oscillator if they are synchronously oscillating, right? And that's something we observe in real life, means there must be some interaction from here. Let's just not worry about this mathematical thing here, but let's just call this entire portion as interaction or coupling, okay? So that's why I'm using word coupling strength here. Sinusoidal, it's just using a sine function. Don't worry about that. It can be another type of function. All to all means each oscillator is interacting with another oscillator. So that's why I'm using word all to all. Now, each oscillator runs independently to its own natural frequency in absence of. So if there is no interaction between these oscillators, then we don't expect them to have something like this. No, because they are independent. So this term disappear like in the first formula. Okay, so this is one way of so the scientist, the chemist actually, Kuramoto tried to explain this synchronization process by using this formula, but there were some limitations. Yes, I can just share you a couple of limitations. Like this mathematical model can be solved if we consider n very large, and that is not realistic because when we talk about, let's talk about fireflies, right? They are limited in number. They are not like in large, of course they are in large number, but that is something we can count, or we commonly use word finite. They have fixed number. So the number of oscillator can't be infinitely large. So there are other limitations too, but that is something we can skip for now. And if we, so I just, when I did some mathematical modeling, I was just using 32 oscillator. You can ignore this entire thing, what is going on, not a problem. But the key thing is when I try to plot, its picture is quite subtle in this y value is that y is actually, it is theta. So theta versus time, how angle is changing over the time. So how these firefly, for example, changing their flashing event over the time. And you say, so some of them, so I'm just labeling these oscillator by unique color. So it looks like some of them are making a close pattern. So they are, so upper part is displaying some common behavior, and lower part at the same time, some of the oscillator are also displaying a common behavior, right? So this is what we call synchronization. They have different independent, they are rotating independently, but the overall motion is some kind of like a group work, right? Collective work. So this is, we can, so this graph may not perfectly describe this natural event, natural synchronization event, but this gives some, at least some idea that mathematically we can also observe these synchronization pattern. Okay, and that is something I did in my study. Now, let me just draw some conclusion of this entire discussion. So oscillators start synchronizing, means showing collective behavior with each other once the coupling between them reaches a certain threshold. So they start interacting with each other. So mathematically, that interaction term we call coupling, that must get some threshold value, like for example, what meaning of threshold, like we pull something, but when we just leave our finger, then it start working, throwing something. Similarly, so they are not interacting, they are not showing the synchronous behavior until interaction between them reaches a value. Once that value reaches, then they start behaving collectively. So if the interaction value is less than the threshold, then they are not going to display such collective behavior. Now, we haven't yet established any mathematical formula that can perfectly describe this natural synchronization event. Physicists and mathematicians, they are working in this field to find a model that can explain this natural phenomena, right? But not yet 100% successful. Various factors are being embedded in original Kuramoto model. So the mathematical relation I was sharing before a couple of slides. It is considered as like a mother formula to mother mathematical model to describe synchronization phenomena. But in when we try to use this mathematical modeling in real life situation, like fireflies, clapping, they are not being so useful to describe these things. So there are other physicists and other scientists, they are trying to add other realistic factor in Kuramoto model so that they can come up with best explanation. And that is something they are working on, we are working on. So this is all about synchronization. It is something can be to some extent explained by physics using some basic idea, but it is something we observe in our real lives. So if you are planning to visit Yellowstone National Park, and there is another park, so you can Google like a synchronization fire of fireflies. If you Google it, then you can probably find the information, exact location where we usually observe these synchronized event. And for clapping thing, you can also try like you can invite a couple of friends, you start clapping. At some point, you feel that synchronous behavior. And so these are something we can observe in our daily life. Okay. Hopefully I gave you some idea of synchronization. So if you have any question, if you need some clarification, or if you want to use some idea of this slide, you are very welcome to send, please send me email. I will be very happy to respond and provide response, okay? Thank you, everyone. Enjoy.